All right, now when we talk about inverse functions, there are some practical applications. For instance, most of us, when we're working, we get paid by the hour. So you could figure out what your wages were by multiplying the number of hours. Yeah, before tax. We'll say wages before tax. Wages is the number of hours you worked, say X times $10 an hour. That might be what you get now. I don't know. Most of you may get about that much if you're working, or maybe even more. I don't know if you're working part-time. Okay, so you could figure out, based on the number of hours you worked, what your wages were going to be, right? Mm-hmm. All right. If you knew what your wages were, could you figure out how many hours you worked?
Yes.
You could. We divide. So really, that is an inverse function. We could divide. If we knew what our wages were, we could figure out the number of hours by dividing by 10. That would give us the number of hours. So these are inverses. Addition and subtraction are inverse functions. Division and multiplication are inverse operations. I guess not functions. They're inverse operations. And today we're going to look at inverse functions. Just like I think this is not a totally new concept. You did inverse functions, sure. But we want to look at a couple of examples. For instance, if I just have the function f of x equals x plus 4. We could represent that function this way. We could represent that function as the graph of a line. We could also represent that function as a set of ordered pairs. For instance, if x is 1, what is y?
5.
5. If x is 2, what is y? 6. And if x is 3, y is 7. If x is 4, y is... And we'll just stop it right there. But that is a representation of the function as a set of ordered pairs. Now, if we want to look at the inverse, when we're looking at the inverse of a function, the domain and range switch places. In other words, the x's and the y's change places. The domain and the range change places. That would be the better mathematical explanation. But for practical purposes, x and y change places. So if I want to look at the inverse of that function I have there, the inverse would be 5, 1, 6, 2, 7, 3, and 8, 4. And the inverse function, the function that's the inverse, and we designate an inverse function this way, the inverse function would be, in this case, x minus 4. Remember, I said that addition and subtraction are inverse operations. Mm-hmm. Well, here on f of x, we added 4 to x. For the inverse function, we subtracted 4 from x. Now, tomorrow we'll look at how to find a different way that we can find an inverse function, because it's not always as plain as this. But what I want you to see is that the x's and the y's, the domains and the range change places. If we were looking at these two functions that I have listed here with these sets of ordered pairs, for f of x, what's the domain? 1, 2, 3, 4. And what's the range?
1, 2, 3, 4.
No.
Oh, 5, 6, 7.
5, 6, 7, 8. Okay, so let me make this a little bit smaller. So let's think about the inverse function. What's the domain of the inverse function?
5, 6, 7, 8.
5, 6, 7, 8. And the range of the inverse function.
1, 2, 3, 4.
So they just switched places. So that, if sometimes you may be asked to find the domain and range, you may need to find the domain of the original function. Once you find your inverse function, you can find its domain, and then you can fill in the rest. Robert,
Today it's just domain.
we said that the domain of f equals the range of the inverse, and vice versa. So the range of f equals the domain of the inverse.
So
Okay.
when does this get hard? 'Cause I know
It really does not get that hard. Now, if there are inverse functions, the definition, because they undo each other, if we took those two functions that we just talked about, let's say we have f of x is x plus 4, and g of x is x minus 4. Okay, I told you that those were they were inverses of each other. But let's see what happens if we take the composite of those functions. In other words, if I take f of g of x and then g of f of x, let's see what we get. So if we're going to do f of g of x, that means that wherever I have an x, I'm going to plug in g of x. So this becomes x minus 4 plus 4, which equals
X.
x. Okay, let's do it the other way. If we do g of f of x, I'm going to have x plus 4 that I plug in for this,
we get.
minus 4, and we still get
X.
x. That is a verification that really those are inverse functions. By definition, when we take the composite of a function with its inverse, we should always get x if they indeed are inverse functions, whichever way we do it. I want an x there. Anytime you take the composite of a function with its inverse, or the composite of an inverse with its function, by definition, we should always get x. And that's how you verify that you have functions that are inverses of each other, by taking the composite of those functions. So let's see. Let's verify these. F of x equals 1/4 x minus 3. And g of x equals 12 plus 4x. That doesn't look as straightforward as those last two we looked at, does it? So we want to verify, are these indeed inverse functions? If they are, what would we get, Zach?
X.
X, if we take the composite of those two functions. If they are indeed inverses, we should get x, and I want to check it both ways. So wherever I have an x here, I plug this in. So we are going to get 1/4 times 12 plus 4x minus 3, which equals 3 plus x minus 3, and that does equal x. Now let's double check it. Let's go the other way. Wherever I have an x here, I'm going to plug in this. So we'll have 12 plus 4 times 1/4 x minus 3. Have to distribute, so we get 12 plus, what's 1/4 times 4? 1x minus 12, does that equal x? So these are inverse functions. They are inverse functions. Okay, I want you to verify whether these two functions are inverse functions. F of x equals 2x plus 4, and g of x equals 1/2 x minus 2. Again, these aren't quite as obvious as x plus 4 and x minus 4, so check to see if these are inverse functions. Both inverse functions, because when we get f of g of x, you got, what'd you get when your final answer? X. And when you did g of f of x, you got x. So they are inverse functions.
Can you not get X for your final answer?
If they're not inverses.
But.
So you may
every
be
time-
asked to determine, are these two functions inverses? If you don't get x when you take the composition, then they're not inverses.
Okay, so the answer always has to be X. It can't be like if you got X plus 2 for one and like X plus 2 for the other. Like it's always like.
No,
X
they are
and
not
X.
inverses. They have to, it has to be the x. Yes, sir.
So it's just f of g of x or g of f of x, and when you put them together, it has to be
Equal to
just
x if they are inverse functions.
Alright.
Okay. Now, when we're thinking about the graphs of inverse functions, with a graph, if AB lies on the function, then BA has to lie on the inverse function. So a lot of times if you graph your function and you're asked to graph the inverse, sometimes the original function's pretty easy to graph. But maybe you don't know how to graph the inverse. If you'll find some points on the original function, you can graph the inverse simply by switching the x and the y values. For instance, it's easy, we just said that f of x equals 2x plus 4, and then g of x equals 1/2 x minus 2. All right, let me see if I can add in here. I think I have some graphs. Guess who got hold of my stuff? Kind of hard to fail your granddaughter.
No, there were pictures of like fail on it. That had like big giant red blocky fails.
Oh, okay, I guess I didn't see those. All right, so if we graph 2x plus 4, using slope-intercept form, we know we go up 4, our slope is 2, and down 2 over 1. So here is the graph of f of x. Let's say I didn't really know what g of x was at this point. This is the point 0, 4, right? And this is the point 1, 6. And this is the point negative 1, 2. So if I want to graph the inverse, I'm going to graph, and that's hard for you to see, isn't it? I'm going to graph the point 4, 0. And I'm going to graph the point 2, 1. And I'm going to graph the point 6. No, that's 2, negative 1, isn't it? This was negative 1, 2. So I have to graph the point 2, negative 1. And this was the point 1, 6, so I'm going to graph 6, 1. And here's our inverse function. Now that looks pretty close. I mean, I didn't get it exactly, but you can see that that should be the graph of 1/2 x minus 2. Our slope is 1 over 2.
So are they gonna like always cross, or are they always gonna be parallel? or just
Well,
like
what
figure-
happens is they always reflect each other across the line y equals x. So if we were to fold them along that line, they should line up.
That's like an axis of symmetry kind of.
Kind of. It is. They reflect, inverses always reflect across the line y equals x. So sometimes that's helpful if we are trying to graph the inverse and its function. So if we wanted to, let me move this out of the way, pull in another graph.
What was called?
Oh, I see where you're talking about.
That's making sure you saw.
Okay, let's graph f of x equals x squared for x greater than or equal to 0. And then let's graph the inverse, which is the square root of x, and see if they reflect across the line y equals x. Okay, so if we're looking for x squared for x greater than or equal to 0, we know we have the point 0, 0. We have the point 1, 1. We have the point 2, 4. And I don't have enough room for 3, 9, but this is the graph for f of x equals x squared for x greater than or equal to 0. Zach, Sean, and Caden, and Robert, sit up. Caden. I know it's hard to stay awake, fifth block, but I have to stay awake, so y'all have to stay awake too. All right, so say I didn't know what the square root of x looked like.
It's like the thing-a-ding.
I know but maybe we forgot. Okay, so we're going to take some points that we know from the function and switch them. So the point 0, 0 stays the same. What about the point 1, 1? It's going to stay the same. Now this was 2, 4. So what am I going to graph on the inverse function? 4, 2. So the inverse function looks like this. And if we check it, that does reflect across the line y equals x. So just a demonstration there. Now notice, when I looked at this function, do you need to stand up? When I looked at the function, I restricted f of x equals x squared to be greater than or equal to 0. If I hadn't done that, I would have had a function that looks like this. A parabola. All right. If I took that parabola, we saw that when we just looked at the right half, we had a square root function. If I took that parabola and tried to graph the inverse, it would probably look like this. But is that a function?
No.
No, that's not a function. How do you know, Sean, that's not a function? Doesn't pass the vertical line test. So we can look at a function and determine whether it has an inverse function by the horizontal line test. The horizontal line test is very much like the vertical line test, but the horizontal line test will indicate to us whether a function has an inverse. In the case of the red function, f of x equals x squared, a horizontal line intersects more than once. So that tells us that it does not have an inverse function. The horizontal line test is like the vertical line test. You can only intersect the function in at most one point for it to pass the horizontal line test. So a function has an inverse function. Let me move some of this out of the way. Is that blue easier for you to see? A function has an inverse function if and only if, I'm going to use my geometry, if and only if no horizontal line intersects more than once. And if that's the case, the function is 1-to-1.
You should do like a neon green.
I don't know if I have a good neon green. Okay, function is 1-to-1 if it passes a horizontal line test. That means that each value of the dependent variable corresponds to only one value of the independent variable. Okay, but anyway, if we were looking at some y'all can see that well? From up here, that doesn't look good on the board. Looks good on my iPad, but so if we had this function, is that function 1-to-1? Andrew, you say yes, no, maybe so? Is it 1-to-1?
It intersects more than once, so
It-
it is 1-to-1.
Okay, it intersects more than once. That means it fails the horizontal line test, so it is not 1-to-1. What about this function? Does it have an inverse function?
Yes.
Yes.
Yes. Is it 1-to-1?
Yes.
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 So
Alright.
if it has an inverse function, then it's 1-to-1.
Yes. If it has an inverse function, it's 1-to-1. If it's 1-to-1, it has an inverse function.
Just check.
Is on page 98. You have 15 through 18, which is some matching. So you're matching a function with its inverse. So find some points on the function, switch the x and y to figure out which one is your inverse. 20, 22, and then 35 to 42. You are determining whether the function has an inverse or not. Tomorrow we'll look at actually how to find an inverse function. But here you're going to be verifying inverse functions. How do we verify an inverse function, Caden?
You verify the vertical line.
No, if we just give it,
Switch, they have to take the x and y lines are switched.
if they switch, you do have inverse functions, but how do we verify that two functions are inverses, Dimitri?
Ma'am,
How do we verify that two functions are inverses?
you can do the horizontal line test. Never mind, that's a graph.
That's a
You
graph.
verify
Each other.
if you compromise them.
Compromise them.
You're not.
I don't think they're compromised, but you take the composition.
Composition.
And if you
yes,
take the composition, what should you get?
X.
X. All right.